Les sons allumés. Et... tac. Là, je te vois. Oui. Ah oui, les speakers, elles doivent être visibles.
Bonjour et merci d'être nombreux aujourd'hui. So I think it will be a seminar in English. So welcome to this new session of a mathematical physics seminar. And today we have a pleasure to hear our colleague Pierfrancesco Urbani, who will talk about the physics of confluent tissues and the Smale 70th problem.
Okay, so first of all, I would like to thank Jeremy and Vincent for the space. So the idea is that I wanted to have a kind of informal seminar because I was working on the things that I'm going to present, and somehow they are kind of paradigmatic, I think. So maybe one can find some kind of paradigmatic application in other things, in other fields. So that's why I was interested in discussing with you. So feel free to interrupt. I would be very basic, very simple things, and I mean it's open to discussion. So okay, so the starting point of this story is in the physics of tissues. Biological tissues. And okay, so this is something that is a research field since long time, and people have worked on this. And more recently, there have been a lot of interest in two things. One is, for example, embryogenesis. And in general, how cells organize into large-scale structures. And the other one, so here in this case, you have healthy tissues. And you want to understand, for example, how they respond to elasticity or things like that. And there is another thing that has been attacked very recently, that is what happens when you have healthy tissues versus tumor. Okay, so here, for example, a lot of people are trying to understand the mechanics of these systems. And in particular, people know that, for example, if you take tumors, you have some kind of core periphery structure in which, for example, the core is more solid-like. The periphery is more liquid-like. And it's from there that you have metastatic formation. So what people want to understand is how you can control the physical properties of this kind of systems.
Liquid, you mean liquid at the scale of a cell? So,
yeah.
So you have many cells, and all the cells behave as a liquid.
Yes. So here, roughly speaking, the mobility of the cells at the boundary is larger than the one in the center. Okay. So, and all this is complicated because the building blocks of this is complicated. These are cells. So they are kind of systems that are active somehow because they process information and they have a metabolism. So all this is a kind of, I call it complex matter. And okay, so what people want to understand is, for example, how you can define a liquid thing or a solid thing, what are the order parameters, what are the control parameters that you can play with, and so on. And of course, you have many tissues. You can have liquid tissues like the blood or solid tissues. The brain is very complex, so there is a lot of variability. And so what I've been interested in recently is confluent tissues. And so these are tissues where cells tessellate space. Okay. So the simplest example is the epithelial tissue. Okay. Very recently, there have been a lot of models that have been developed to study numerically these kind of things. And okay, I will not review all the models, but I will focus on one of them that is called Voronoi model.
Sorry. I had a question. What is epithelial tissue?
The skin.
The skin.
Okay, so what is this model? So what we want to model is some kind of system in which you have cells that translate the space somehow. And so you would like to have some kind of construction that gives you a tessellation. And the simplest construction is the Voronoi construction. So what you do is that you throw at random points in space, and you do the Voronoi tessellation. So what is the Voronoi tessellation? So you partition the space in such a way that, for example, this point is the closest to this one. This point is the closest to this one. And so you partition the space according to which point, which center of the cell is the closest to you. Okay. Okay, so what is this model? So you are given endpoints in space, let's say in R to the B, in D dimension, and you construct the Voronoi cells. And these are the cells of your tissue. So these are convex. They have convex shape, but and I will play with the shape in a second. Okay, so now what do you do with this? So you just invoke some biological constraint, and you say, okay. So for each cell, I can define its volume. Let's say that this is the center of the cell I. So let's call xi the center, the point from which you do the Voronoi construction. And for each cell, I have some volume and some surface. And then you say, okay, just because of metabolic reasons, the volume cannot be arbitrarily large, because I mean, if the volume is large, it means that the metabolism is big, and maybe this is not very good. And even the surface maybe cannot be too large too, because this is a phospholipid membrane, so it has a limit of stability. So you would like to have these two things that are kind of controlled. And so, okay, so how do you enforce some control on this? Well, you define some cost functions in which you impose that the volume and the surface of the cells would like to attain some target value. Okay. So, and this is
perimeter.
Sorry?
Perimeter.
You can also impose the perimeter. Yes. So in 2D, for example, you have area and perimeter. You can even impose that maybe the volume is free and the surface is constrained. So this is a very generic model. And the quantities that you use to build the model are important. Yes.
In your Voronoi model, you have no curvature. Each
No
one
curvature.
is
The corners.
apart of the corners, but they are
Yeah, these are straight lines or surfaces.
Yeah.
Okay. Yeah, okay, you can generalize this to other tessellation models. Okay, so this is really the simplest one. Okay, so you define a cost function. And you say, okay, for each cell, I would like that it attains a target volume and a target surface. So you say, okay, let me define this square loss function.
Or you want to put a square.
Okay, so this is just a square loss function, and it has no, for what I know, no biological meaning, rather than saying that you want to have a model in which volume and surface try to obtain some target values. But so you can use other form of viscous function. And okay, so this is what people have been using in the last, let's say, 5 years. Okay, so what people do now, they try to study the dynamics of this model. So they say, okay, so I have a cost function. Let me define some dynamics for the cells. So each cell has a center xi. So let me define some dynamics for the xi. So, and the simplest one is some kind of stochastic dynamics. So each cell is trying to minimize its cost function, and then I add some noise. Okay, so the noise can be of two types. Let me put it here because then I will not use it anymore. So you can take, for example, at I to be some Langevin noise at a given temperature. So this is equal to 0. Okay, so this is Langevin noise at a given temperature T. Or what people are more interested in is the case in which the average is still 0, but the 2-point correlation function has some non-trivial structure. So delta J, and then some gamma of t minus t prime. So for example, you can take gamma to be some exponential. So this means that you add some noise that has some persistence time tau. And this is, so these people say that it's an active model, so it's an active matter model. Okay. So in general, you have two terms. This one is essentially taking into account elasticity. And this one is noise. And the strength of this term, let me call it T in both cases. Okay. So when I say that T is going to 0, it means that I'm removing this term. So this is one of the two control parameters in the problem. And there is another control parameter. So this one is rather standard. I mean, I have some Langevin dynamics, and this is just the strength of the noise. So this is a standard control parameter. And there is another control parameter that is not that standard, that is called the shape index. Yeah, maybe I write it. So this is, let me say, so one is noise strength. And this is rather standard. And the other one is called shape index. So in the Hamiltonian, you have two numbers, that is the target volume and the target surface. So you can build an adimensional number. Let's call it B0. It's just the target surface divided by the target volume to over D. And so this is a control parameter. And so what you can imagine is that if this control parameter is large, then essentially you are promoting shapes that are of this kind, because you have large surface with respect to the volume. And instead, when this is small, essentially you are enforcing that the shape of the cells is more compact. Okay.
By the way, you don't want to put any parameter into H. I mean,
Yes, in principle here you can put some elastic constants. Let's say KV and KS. But for what I will say, these are not very important. So I didn't just to say the simplest. Okay, so just based on this, what you can imagine is that in this case, the system is more liquid, just because since cells can squeeze, they can diffuse. Okay, so if I switch on some dynamics, some noise, in this case, I expect that the system is liquid-like. And here, in this case, I'm putting tension at the level of the cells. And so this will be some solid-like system. So this is just naive expectation. Do you agree?
I thought that the tissue grows, and if it grows, then it's not described by this kind of dynamic.
No. So I'm taking the size of the system fixed. So I have n cells inside a given volume V.
Okay, no, I understand that, but does it correspond to any physical situation? Any biological situation?
Well, I mean, here I'm not putting growth or apoptosis, or I'm just studying this system and whether it's solid or liquid, if there is a phase transition in between. So really the simplest thing, yes.
Could you give? I got confused. So imagine a fixed volume.
Yeah.
A fixed volume. So the different picture which you have below corresponds to the minimal area and the maximal area for given volume. So if I fix the volume, I fix the denominator, then you think I'm going from
Yeah, exactly. So,
I would expect that the largest volume, largest area correspond to given volume should be sphere.
no, that's the opposite.
it's the opposite.
It's the opposite. It's largest volume for a given area is the sphere.
Largest volume for given. Okay, and then if you go green, then if you go to the maximal area for given volume, it should be like branching polymer or something.
I don't know. I don't know.
No, but just to get idea, what you
So okay, so I can tell you what people do. What people do is that they take this, okay, they fix V0 to be, let's say that you are in large V, so V is big volume, then you take V0 to be V divided by N, just the average volume per cell, and then you play with H0. Okay. So this defines some. So, and then you play with that. Zero means that you run this dynamics on a computer. Okay. So what do they observe? So by the way, the model is defined in any dimension. So it's totally.
And when you say you throw the points to start with, you throw the points randomly.
Yes.
Place it's uniformly.
Yes.
It's uniform.
Yeah, exactly. Yeah. Poisson distributed, etc. So. Sorry?
in the rock case. Why is it liquid like?
Well, just because you think that, okay, at least for me, I just think that cells can squeeze, and there is no tension within them. So here I'm just putting some tension at the level of the cell that essentially spreads all over the system and gets, so you have a system that is under tension in this case. Here, I mean, you use the local tension and the system is more liquid. But okay, so this is a kind of naive expectation that I get after reading the paper. So,
Is there a stationary state when you wait long? Or?
yeah, okay. So let me discuss the stationary state of the dynamics. So people did some numerical simulations. There is a paper by Manning et al. I think 2016, if I remember correctly. And okay, here I put P to be the strength of the noise. Okay, and this depends on the particular shape depends on what noise you take. But okay, the phase diagram is more or less the same for all of them. Okay, so here I put T and here I put P0. Okay, and they found that there is some kind of line. So above this line, the system is liquid, and here is solid. And what I mean by liquid, I mean the following. So I can define some mean-square displacement. So this thing has different shape depending on whether you are here or there. So this tells you how much I'm going far from some initially taken configuration. So in this region, this behaves like this. So it reaches a plateau. So essentially, cells are trapped; they don't diffuse. And in this region, there is no, so you diffuse away. Okay. And there is a lot of interest in what is the particular shape of the dynamics here, but okay, there are essentially simulations. Okay, so this is what I mean by liquid and solid. And okay, the last thing that I want to say about this is that the solid here has no particular crystalline order. So it's a kind of amorphous structure with no order at all.
Wouldn't you expect them to form some sort of like hexagons or something?
Okay, so hexagons are formed if you do some kind of annealing, slow annealing, but even that hexagon structures are kind of rare. Okay, so people find mostly some amorphous things. Okay, so the question now is, what is this line? Can you characterize the phase transition? What it is critical? There is some length scale and so on.
What about D? Sorry.
Yeah.
What about?
This is for what dimension?
People have found this in D equal 2 and 3. But I think that there are also simulations in 4. And okay, let me say something that in D equal to 2, this is kind of special in the sense that, okay, and this is important for what I'm going to say next. So you see this line, it goes up to T equal to 0. What I mean by T equal to 0 is that I mean a specific thing in the sense that I switch off this noise term and I start from a random configuration and I do some gradient descent. Okay, so if I switch off this thing, I initialize, so xi at time 0 at random, and I look at what happens at the end of this dynamics. So this is some gradient descent, it will reach some fixed point for h. Okay, so if I do this, so at t equal to 0, it is found that in d equal to 2, there is no transition here, and actually this line goes like this. Okay, and so this is in a paper by Merkel and Sussman. while in D equal to 3, you have a true phase transition. And what I mean by phase transition is the following. So let me discuss what happens when I switch off the noise term.
Sorry, which order of transition?
It's complicated. Let me just describe what happens. Okay, so I take t equal to 0, which doesn't mean t going to 0, first thing. So I just do the following. So I run this dynamics. So I take this at random. This is random, taken uniformly on the space. And then I run this dynamics up to when the dynamics stops, because as soon as I find a stationary point of H, this stops. And then I look what are the properties of this point as a function of the only control parameter that I have, that is speed 0. Okay. So I have some phase diagram that is in 1D. So this is speed 0. Okay. So this phase diagram is not there if I take d equal to 2. Let me just forget for a moment d equal to 2, but let me consider 3 dimension. So I have a critical point that separates two phases. And okay, what are the properties of these two phases? So if P0 is smaller than P0 star, so the endpoint of this dynamics is a local minimum of H, but this local minimum has a positive energy. So H infinity, let me call it. And okay, so it's a local minimum. I can, for example, look at the spectrum of the action in this minimum. So I can define some action. And I can look at the eigenvalues of this matrix. And the eigenvalues of this matrix are all positive. And the spectrum looks like something it has some shape. Okay, so let's do the omega, the of omega. So omega is the eigenfrequency. And in log-log plot, it looks like something like this. Okay, so it has a shape at small omega that is omega to some exponent, which is still unclear from numerical simulation. But all eigenvalues are positive, so I'm just in a local minimum. Okay. And okay, this local minimum is a kind of amorphous minimum, so it's a kind of glassy minimum with no structure whatsoever. Now, if you take P0 greater than this critical point, is that things change, because I get to a zero energy configuration. Okay. So what does it mean? So remember that H is oops. So it means that for I, so it means that each cell attains the target volume and shape. And I can play the same game, so I can define the action at the point that I'm finding, and I can look at eigenvalues. So if I look at the spectrum of this matrix, typically it has this shape. So okay, let me not impart on this, but the row of lambda contains a delta peak at lambda equal to 0 plus some, and it has a regular part. Okay, so this matrix has a delta peak of 0 eigenvalues plus some regular part. Okay, so what does it mean? It means that here you have a kind of zero energy manifold in which the system is able to attain. So if I look at the landscape of this cost function, it looks like this. So it has, okay, now complicated, but okay, let me do it. So it has some kind of shape like this. So it has a zero energy manifold. And this zero energy manifold can be found just by doing gradient descent.
So is P0 corresponds to the sphere in the dimensions, or is it greater than that?
Sorry,
well, I guess it has to be true that you can compute the value of P0, which corresponds to the d-dimensional sphere, which is basically the spherical shape. And in dimension, you can compute the volume and the surface of the sphere. It is going to correspond to some volume of P0.
So when the cells are spheres. No, it
has to be the case that P0 is greater than.
Yeah, it's large.
It's straight line.
Yeah, it's strictly large. Yes. Yeah, of course you can bound P0 by just the most compact shape there is the sphere, but it's definitely large. And actually, this P0 it depends a bit on the algorithm that you choose to minimize the H. So for example, I just discussed gradient descent, but you can do something else, and the value of P0 it changes numerically. So it is not something that is universal in any sense. I mean, it depends on the dynamics. Okay, so for me there are two.
That's all one. You see, if you to the right for P naught star, then you have some zero mode, which affects the energy, which drives your kind of system in some.
It's flat. It's flat on a manifold.
It's flat in the direction.
Yes. And this part, so this C is order one. So this you have an extensive number of zero modes. Okay. Okay. So for me there are two conclusions that are.
Is it correct that C depends on P0?
C depends on P0. Yes, of course. Okay. So to me there are two conclusions that are. Okay, maybe trivial or trivial, I don't know, but first that there exists this manifold and you can find it. I mean, the fact that it exists, maybe it's not so, okay, I don't know if it's interesting or not, but that you can find it. And just by doing some gradient descent.
For each of these points, classical configuration corresponds to it, right?
Sorry?
So for the any value of P naught, you have particular classical configuration which minimizes your function.
Yeah.
So you said that to the left from P0 star, you have kind of code solid.
Yeah.
And then you go to the right, what you call liquid.
Yeah, I mean,
what does that actually mean? Since you know classical configuration, you have this particular zero mode. What does the zero mode? What actually does the level of the surface, the level of cells?
So okay, so the thing is that okay, in this region essentially you have this zero energy manifold. So if you give some little kick to the dynamics will just surf on this manifold. In this case,
I'm saying that if you just look for the configuration of the cells which cover your, let's say, dimensional space. So if I turn on the zero mode, so the zero modes will correspond to some deformation of
yes.
What kind of deformation it corresponds to?
No? It's a deformation which leaves these constraints unchanged. So okay, and I mean there is no symmetry whatsoever that gives you the deformation. A kind of random manifold at this level. To me, it looks like a random manifold. Okay, so I wanted to have some basic model of this, and because okay, there have been a lot of works. Many of them have been numerical, trying to study these kind of things and the dynamics associated to that. And I wanted to have some kind of simple models that I could play with that has exactly the same structure. Okay, so before telling you the model, let me just take very trivial things. So how do you you can rationalize this? So let me just do some constraint counting. So I have an Hamiltonian that is trying to enforce some constraints that are this. So how many of them I have? So if I have n cells, I have 2 times n constraints. That are nonlinear, and this is important. Because the volume and the surface are nonlinear functions of the positions of the Voronoi points. So I have 2 times n nonlinear constraints, and then I have d times n degrees of freedom, that are the coordinates of the Voronoi points. So if I want to have a system that admits a zero energy manifold, naively I have to say that I need to have that the number of degrees of freedom is larger than the number of constraints. And this is why in d equal to 2 you need to be a bit more careful. Okay, but in d equal to 3, in principle, there is no theorem on the existence of this zero energy manifold. Maybe this is very clear. Okay, so I wanted to have a simple model for this, and okay, so I just made a Mifflin model. Okay, so let me just define a toy problem. Okay. So toy model. So the model is very simple, and okay, surprised that okay, maybe it has been discussed already, but I don't know, and I've discussed also with other people. It seems that it's was not discussed in the literature. So okay, so since from this perspective of constraint counting, I would like just to find a model in which I have a set of nonlinear equality constraints that I would like, and a set of degrees of freedom that I would like to find in order to satisfy all constraints. So let me define this model. So I have a set of degrees of freedom, so it's an n-dimensional vector. Okay, so the components are real, and then I just to have a compact phase space, I just fix the length of this vector to be equal to n, such that each component is over the 1, typically. So these are my degrees of freedom. And then I would like to construct a set of nonlinear equality constraints. So what I do, first I define a set of random matrices. Okay, so these are n by n random matrices, symmetric. And the index mu is an index for each matrix. So I have m big M random matrices. So each component is a normal variable, so zero mean and unit variance. And how many of these random matrices do I have? I consider m to scale with n with some proportionality factor, alpha. That is a control parameter in the flow. Okay, now I can define some nonlinear constraints. So let me define a variable h mu. So it depends on the matrix that I'm considering. So this is a nonlinear function of the x, of the degrees of freedom. And the factor 1 over n is such that this thing is of order 1. And okay, so this variable morally plays the role of volume or surface. Okay. And so the constraints are just that I would like to find the variable x's such that h mu is equal to p0, that is a control parameter that I can decide. And so which plays exactly the same role as the shape index in the original model. Okay, it's a totally random model, totally abstract, but which morally looks like similar to what people have been doing in tissues. Okay, so the idea is find that such that this is true for mu. Okay, so and I play the same game that people have been playing. So I define some cost function to enforce this constraint. It's just the square loss. So I have two control parameters. So I have this P0, that is the shape index. And here I just generalized the model, and I have a number of constraints that scales with the number of degrees of freedom. So I have P0, that is morally the shape index. And the other one is alpha, so the density of constraints. And this alpha, in the original model, it depends on the dimension of the model. And here I can just take it as I want. And even in the original model, in principle, I can decide to remove some constraint. For example, I can decide to remove the volume constraint. Okay, so if I do that, for example, in 2 dimensions, I can have a phase transition of 0 temp. Okay, so this alpha is something that can be tuned even in the original model. Okay, so this is a model, and there is a natural generalization. So here I just consider a quadratic function of the degrees of freedom, but you can do something different. So you can generalize this. So here I just consider matrices, but then you can generalize tensors. You can take, for example, h mu would be okay. So these are different objects, of course. I mean, if they have different indices there, they are different. And so on. Okay. So and this is just by choosing these coefficients here, I can essentially get some kind of random field with correlations. So this field is Gaussian, and it has these correlations. And here I can take a function g that has the properties that is such that this is a two-point correlation. So this is just the scalar product between x and y. Okay, and g can be whatever I want. So the model can be generalized to any random field. Okay, so okay.
Is it important that the indices don't take the same value? Because you sum only over.
No. Okay, no. In principle, you can also sum the other. I mean, it's just a factor in front. I just do it this way because it's more clear in my mind when you do computation. So, but yeah.
You can also include diagonal terms and the average of each neighborhood.
Yeah. So yeah. Okay. So yeah, if you include the diagonal term, you add some constant term in the average. But let me consider the case in which there is no constant term. Okay. So.
Sorry, why rotational invariance?
Because this is this rotational invariant descends from the properties of these matrices and tensors. Since I'm taking everything that is totally rotational invariant, the probability distribution of these things, then I get something that is rotational invariant.
Okay.
If I put some structure on the probability distribution of these objects, then this is no more true. Okay. But this rotational invariance is what is very useful when you try to solve the model. Okay, so the model can be solved, and okay, you can study it even within numerical simulation. It's very easy. And so what I did is first I studied the model, the thermodynamics of the model. So let me. So what I do this. Okay, so what I did is that I just defined some Gibbs measure. Okay, let me just write it this way so that I. And H is this, okay? So this is the Gibbs measure over the sphere. So remember that I put this constraint. Okay, I can define some partition function. And define the free energy. And so what I'm interested in, so this beta is the inverse temperature. Now this is really a true temperature. So I'm supposing that the system is in contact with a bath. And I can study this measure, this probability measure, as a function of beta. And I'm interested in two limits. So first, I'm interested in the thermodynamic limit and also the zero temperature limit, which concentrates this measure on the zero energy points of the Hamiltonian, if they are there. Otherwise, it will be just the ground state of the problem. Okay. Okay, so not sure. Okay, so this thing can be studied. In particular, so this measure is a random measure because it depends on these matrices and tensors. And so what you would like to understand is what is the typical behavior of this measure and the free energy. So typically what you do, that's what you typically do in disordered system, you consider the average of this over the realization of the J's. And this will give you the typical behavior of a sample. So this thing can be studied through the replica method and so on. And okay, so let me just write the phase diagram that I get. So this is a function of P0, okay, and I'm considering really beta that is going to infinity. Okay, so okay, now I'm just cutting all the technical details that maybe I can give in 2 minutes. So I have a phase diagram. That is the phase diagram of the zero temperature limit of this Gibbs measure. And what I get is that I have 2 phase transitions. So first of all, so the way in which I constructed the model for large P0, it means that I'm going to the solid phase. It's the inverse of the original model. That's the only qualitative difference. So here the model is solid-like, and here it's liquid-like. And so I can compute this phase transition point between the liquid and the solid part. So here H, so H infinity means H of that is equal to the ground state. This is positive. Here H is equal to 0. And I can compute the critical point. So what is this point? So at this point, I know that this measure is no more concentrated on zero energy configurations. Okay, so below this point, this measure is spread over zero energy configurations, while above it, I have some ground state of positive energy. Okay. Okay, so here it means that I have some zero. So a zero energy manifold exists. And okay, the properties of this measure change when you change this P0, and in particular, you have some transition here. Okay. Let me call it P0G. So in particular, what happens, so you can look at the structure of this manifold. It's a high-dimensional zero-energy manifold. And for small enough P0, it's some kind of ergodic manifold. So you can essentially equilibrate this measure. And above this point, you have this ergodic manifold splits into different pieces. Okay. And technically, here the model is, okay, replica symmetric. Here you have replica symmetric breaking.
How many steps?
So this is full RSB, which means that in order to find this point, you need to solve a set of PDEs. Okay.
This picture is independent of the parameter alpha.
So, true, thank you. So this is for, of course, for alpha less than 1. So what I did is that I compute this phase diagram for alpha equal to 1/4 as a function of P0, but you can fix P0 and change alpha and so on. So I didn't do the full computation of the phase diagram. So, okay, maybe I can say, so this just tells you that there is a manifold that you can study its geometry. And okay, now the geometry is directly related to this Gibbs measure, but you can do also another thing, that is studying dynamics. So I started with the Hamiltonian, and then I say, okay, I switch off the noise term, and I just look at this gradient descent dynamics. So do I find some zero energy configuration? So here I can do the same. So you can study this. Okay, let me just write this. So I just add some Lagrange multiplier in such a way that I can fix the spherical constraint. And this can be studied in the Lagrange limit. So it's an exactly solvable Lagrange model. And okay, so I don't know. Okay, so in the end, you can solve the dynamics of this problem, and you have some Dyson equation where you can compute exactly the self-energy. Just needs an exact expression. Okay, and once you solve it numerically, you can, for example, look at the behavior of the energy as a function of time. So as time goes by, you can compute the average value of this energy, and then you can show that in this region, even in this glassy-like region, this algorithm is able to find a configuration at zero energy. Okay, so if you look at the energy, this relaxes exponentially fast up to some region that is nearby this thermodynamic satisfiability transition. Okay, and why this is interesting? Because, okay, first of all, to me it's not obvious. It's a Lagrange model. You can have course of dimensionality, so you can have that this algorithm gets trapped in local minima that certainly are there. But no, actually, if you start it at random it is able to find a zero energy configuration. And since the energy relaxes exponentially fast, it means that this algorithm is a kind of, it means that you can find a zero energy configuration in polynomial time between the system starts. Okay. And okay, so what is the connection with the Smale problem? So the Smale problem, so Smale was asking whether you can find a solution of n complex equations in n unknowns and in polynomial time. Okay, when n is large and when you have given a probability measure over the polynomials. And okay, so this is a kind of baby version in which I have some measure over polynomials, so the H neural polynomials. It's on the reals, but this shows that essentially you have a polynomial algorithm, and this polynomial algorithm may be not optimal, so its threshold may be slightly different than this with zero, but there is certainly a region where I can easily get solution in polynomial time. And this region has nothing to do with this transition here. Okay. Okay, so I don't know, maybe I don't have time. So what I did next is that I for reasons that have nothing to do with biology, I quantized the model. So I said, okay, let me add quantum fluctuations to the model, and I studied the phase diagram. But okay, if you are interested, I can tell you, or since sorry? Okay, so what I did is I said, okay, for reasons that okay, maybe it's not to explain, but okay, so I consider another model. So now I say, so these variables are operators, and so I have momenta. Let me say that. So now this is an operator, and then I can study again the partition function. Okay. I can study a trace this H. Okay. So this gives a path integral that is dominated by a Lagrange a saddle point. So it's a Lagrange model that can be solved exactly.
Sorry. Where kinetic 10 came from?
I just added and I impose this.
No, but then the first equation is contradiction of the second one. first line and second line annotation.
First one.
This one.
This one and this one.
Yeah, so the second
No, this one, this is the classical model. Let's forget.
No, but when you're saying you go to the quantum, going to quantum model, you just put canonical term. I'm asking the reason why you put canonical term in quantum model. You didn't have in classical.
In the classical model, it would be pi equals 0.
Yeah, so I mean, I'm just removing this, and then I just consider this operator. Okay.
Hamiltonian, maybe it's my fault. Hamiltonian equation is p dot with minus h over here. First equation should be p dot.
Yeah. This is not Hamiltonian. This is just overdamped equation. I mean, it's very in the sense there is nothing. I mean, it's not Hamiltonian dynamics. Okay, it's Lagrangian overdamped dynamics and so on.
You're trying to solve the equations of motion for the Hamiltonian, you're trying to find the minimum of the Hamiltonian.
Exactly. So let's forget this. I just define this operator, and then I can study this. This I can. This is purely quantum, and I can tune h bar. Okay, so this can be solved exactly. So you take the partition function, you write the path integral, and the path integral is dominated by Largen. So it's a Largen model can be solved, and you can look at the phase diagram. So again, I have this peak 0, and now I have this is true temperature, so this is 1 over beta. And okay, so I have here somewhere the phase transition P0 star. So classically, above this point, the landscape of this age is some kind of glassy landscape. Okay, and below I have this zero energy manifold. And I have this point here, with P0G, that separates a region in which, in principle, classically, I can sample past this Gibbs measure. Okay, so the sampling time of this Gibbs measure is fast. And beyond this point, it becomes harder because the landscape of this manifold is kind of glassy. Okay. So classically, so if I take h bar equal to 0, I have some line here above which essentially the system is above. So okay, so it's replica symmetric means that I can sample fast the Gibbs measure, and below this line, this sampling slows down. And now I can add quantum fluctuations. And okay, so maybe I should write it better because otherwise I cannot see the figure. So if I add quantum fluctuations, the naive expectation is that when I open quantum channels, I can do tunneling. So if here I have some glassy landscape like this, so classically I need to jump the barrier, but quantum mechanically I can do tunneling. So in principle, this line where the quantum dynamics feels glassiness, so this line should go down, right? Because if I open relaxation channels, then it means that this line should go down. So this happens if I take P0 very large. But if so, and I can do it for various h bar. So this line is the h bar equal to 0, and I can increase h bar. And here, essentially, this is true. So adding quantum fluctuations helps me to thermalize the system. But then at some point, if h bar is not too big, I start to see this. So I see a crossing exactly around the point where this zero energy manifold doesn't exist anymore. So there is a region here in which essentially moderate small quantum fluctuations induce some glassiness in the system, so I cannot sample essentially past the Gibbs measure. And to me, this is counterintuitive. So, okay, so of course, this happens only if H bar is moderate, is not too big. As soon as I increase a lot H bar, this line shifts like this. So this is for H bar much larger than 0. So there is a non-monotonous behavior in H bar. And this was found also, for example, people were considering glacier spheres and tuning the H bar. And they were seeing that when our spheres are very packed, just adding a bit of quantum fluctuation induces glassiness. So the second thing that I want to say is that, and the last thing is that, so if you take this model and so you can look at the zero temperature limit. And so here there is a point. So at finite H bar. And I think that here, if you look to this correlation function, so this behaves as a power law in this Matsubara time t. So okay, I'm sorry, but okay. So I take the zero temperature limit. So I have a path integral over some imaginary time. And then if I look at this correlation function, this decays as a power law at this point. And I don't know the power law because I didn't study the Landau theory close to this point. But to me, this is very close to what happens, for example, in SYK models or things like that. So, okay, so to me, this is a kind of model in which I have some zero energy manifold in high dimension with quantum fluctuation. It's a kind of billiard, high dimensional version of a billiard. And then here you can study, for example, I don't know, chaos, things like that. So this is one of the reasons why I was interested in this model. So, okay, maybe, sorry for taking so much time. This resonates with something that you do. I'm happy to discuss.
Other questions?
No, this is the last point you mentioned. H bar is dimensional. Another dimensional parameter is T. There is no more dimensional parameter. How could be? Because you're saying that H becomes too large and too small compared to T, right?
Yes.
So then how could you have these different curves?
Well, I have also P0, right? Yeah, this control parameter.
Oh, right.
And that's the thing. I mean, yeah, so yeah, to me, actually, visualizing this is a bit more complicated than visualizing, for example, R spheres. So imagine that you have R spheres bouncing around. You can consider the classical model or the quantum model. And what has been found is that R spheres become glassy. This is just numerical, some numerical integration. They become glassy when you add the moderate quantum fluctuation. And they become glassy close to this random cross packing point where R spheres generate. And here it's the same, exactly the same phenomenology. I mean, the model is very different from R spheres, but the overall picture looks similar. And there should be some, so the value of H bar at which, for example, this doesn't happen anymore should have some link with the structure of this energy landscape. So I have a rough zero energy manifold in a dimension with some hills and so on, and the height of the hill should have something to do with the H bar at which this phenomenology disappears. So I'm just playing with quantum fluctuation to probe non-locally zero energy manifold. So it's a way to probe the manifold via quantum fluctuations. And actually, there is a link between these, so if you take the quantum mechanical model, if you do a little bit more work, for example, you can study the geometry of the zero energy manifold. So you have configuration at zero energy, and then you can ask whether I can connect two of them staying at zero energy. So this is a kind of instanton problem in a dimension. And the baby version of the instanton problem is the quantum model. So that's why I studied it.
Pierfrancesco again.
Thank you.